Welcome, engineering students, to this interactive 3D guided explainer. I'm thrilled to be presenting this today on behalf of Assistant Professor Dr. Ramani Bai Vardharajan, alongside Mr. Taha Mohammed Jassim, right here from UCSI University, Kuala Lumpur. Whether you're studying mechanical, civil, or industrial engineering, mastering the basics of stationary bodies under forces is absolutely crucial. So let's step into our virtual lab and get started. Here's our game plan for today. We'll start with a welcome to statics, then move into real-world challenges, do some step-by-step mixing, run the compressive test, tackle calculating strength, and finally wrap up with a core concepts quiz. All right, let's jump straight into part 1. Welcome to engineering statics. We're aligning this lab practical perfectly with your core syllabus outcomes for DMEX 1084. Everything we cover today directly applies to the real world. This explainer is going to help you visualize the basic mechanics of stationary bodies under the action of forces. You know, statics really isn't just about scribbling equations on a chalkboard. It's about predicting exactly how materials will behave under continuous stress. This is going to directly prepare you for your lab reports, your continuous assessments, and, of course, your future careers. The main takeaway here: mastering rigid bodies is the literal foundation of structural safety. Keep that in the back of your mind as we move forward. Which brings us to part 2, real-world concrete challenges. Before we even touch the virtual equipment, we really have to ask ourselves, why do we go through all the trouble of testing concrete in the first place? I mean, why does this specific material need such rigorous daily testing? Well, the crucial point is that undetected flaws in your mix ratio, whether it's an off-water cement ratio, poor compaction, or just incorrect curing, can lead to massive variations in strength. If those go undetected, they completely compromise structural integrity. In modern industrial maintenance, this test is quite literally a life-saving daily practice. It prevents catastrophic failures in the buildings we live in and the pavements we drive on every single day. Just ask yourself, what happens when a pavement fails under heavy daily traffic? That exact disaster is what we're learning to prevent today. Moving right along to part 3, step-by-step concrete mixing. Let's see how this all builds in our virtual lab, going step by step, starting with the concrete mixer. Watch the 3D animation on your screen as we prep the machine. First, we have to ensure the mixer drum is completely clean. Then we accurately weigh out our cement, fine sand, coarse aggregate, and water. Now here's a critical tip. Always turn the mixer on before adding materials. We add the dry materials first and let them dry mix for exactly 1 minute. That step is absolutely vital to ensure uniform distribution before any chemical reactions even have a chance to begin. Now, check out the water integration step. We gradually add the measured water while the mixer rotates. And the golden rule here? Never, ever add extra water. We let that mix for another 2 minutes. Once you can verify a nice, uniform color and consistency, you discharge the mix onto a clean, damp tray. From there, we perform a slump test for consistency and cast the concrete into our molds in 3 compacted layers. So, to summarize this whole section, precise mixing plus no extra water equals a totally reliable test specimen. Next up is part 4, the compressive strength test. Okay, so our mix is cast into standard cubes and it's been cured for specific time frames. Now, it's time to test its breaking point. This is where statics truly comes to life. Think of this as the ultimate test of equilibrium that we study in your lectures. Compressive strength is the direct measure of hardened concrete's ability to withstand axial loads. Simply put, just how much continuous crushing force can this rigid body take before it fractures and equilibrium is completely lost. Visualize the universal testing machine applying a steady compressive load in real time. Safety always comes first, so we always close the machine guard. We bring the upper platen into contact with the cube, and we apply the compressive load continuously, without any sudden shocks. Once the cube breaks, we record the maximum failure load in kilonewtons. It is incredibly important to observe the failure pattern here. You know, did it crack symmetrically, or did it fail diagonally because it was positioned incorrectly? Now look at this real lab data from our tests. Cube 1, which cured for just 7 days, failed at 55.11 kilonewtons. But Cube 3, which cured for 14 days, held on until a massive 186.54 kilonewtons. That is a monumental leap in load capacity, purely from giving the cement just a little more time to chemically cure and harden. Let's dive into part 5, calculating concrete strength. Seeing the machine crush the concrete is definitely exciting, but let's grab our calculators and transition from physical testing over to theoretical statics. How do we actually turn those kilonewtons into standardized pressure? Well, the core statics formula here is beautifully simple. Fc equals P divided by A, meaning compressive strength equals the maximum failure load divided by the cross-sectional area of the loaded face. This equation is the absolute bedrock of material strength calculations in civil and mechanical engineering. Let's quickly break down the necessary conversions you absolutely must remember for your exams. The math requires precise units, guys. Your load, P, is recorded by the machine in kilonewtons. You have to multiply it by 1,000 to convert it into standard newtons. Similarly, your area, A, must be carefully calculated in square millimeters. Take your time with these conversions. A single misplaced decimal here can compromise an entire structural assessment. Let's walk through a quick example together. Imagine a standard 150 millimeter cube fails at a maximum applied load of 675 kilonewtons. First, we find the area. 150 times 150 gives us 22,500 square millimeters. Next, we convert the load. 675 kilonewtons becomes exactly 675,000 newtons. Divide 675,000 newtons by 22,500 square millimeters, and boom, you get exactly 30 newtons per square millimeter. And since 1 newton per square millimeter is perfectly equal to 1 megapascal, our compressive strength is exactly 30 megapascals. It's really that straightforward when you follow the steps. To summarize, carefully convert your units to newtons and square millimeters, and your strength will flawlessly calculate into megapascals every time. And finally, Part 6, Core Concepts and Quiz. To make sure you're totally prepared for your DX 1084 continuous assessments and final exams, let's wrap up with a rapid-fire lab quiz. Let's see how well you can apply these engineering statics principles. Question 1. Think back to the comparison between the 7-day and 14-day cube tests we looked at earlier. Why does the load capacity jump so dramatically just by waiting a few extra days? The answer? It's all about the chemical hydration process. As cement continues to hydrate over its standard 28-day curing cycle, the concrete matrix becomes significantly denser. This denser matrix creates a much stronger internal bond, making the rigid body capable of bearing vastly heavier axial loads before fracturing. Moving right to question 2. Why do civil and mechanical engineers insist on running this specific compressive test on every single job site in modern industrial maintenance? Well, it prevents absolute disaster. This test mitigates the risk of catastrophic infrastructure failure under load by catching undetected inconsistencies, like a bad water-to-cement ratio or poor compaction. Those flaws would otherwise remain totally hidden inside the concrete right up until a building collapses. It is our ultimate safety checkpoint. Last one, question 3. Let's test your statics math backwards using the formula we just learned. If you have a 100 by 100 millimeter cube and you really need it to achieve a target compressive strength of 25 MPa, what must the minimum failure load, P, be in newtons? Let's work it out together. The area of a 100 millimeter cube is 10,000 square millimeters. We already know 25 MPa is 25 newtons per square millimeter. So, rearranging our formula, we just multiply the area by the required strength. 10,000 times 25 gives us a required failure load of 250,000 newtons. Mastering these calculations is the absolute foundation of structural engineering, which leaves us with one final provocative question as you head back out into the lab. As we continue to build taller, heavier, and way more complex structures, are your concrete mixes mathematically strong enough to support the cities of tomorrow?